Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Sempai. Welcome back, everyone. Today we're jumping into a 12th grade topic, continuity and limits. Now, if you're new to my channel, I'll be putting time codes in for this video in the description box below, so use that to skip ahead to whatever part of the video you think is most interesting. As always, if you have any questions about what you see today or even your own homework, you can always put in the comment box below or visit my Facebook page at Tutor Me Sempai and tell me all about it there. At the end of this video, I'll be linking my 12th grade playlist, in which I cover a lot more topics. So if you're interested in that, make sure you stay tuned. This video is going to have 3 parts, so leave a like, smash subscribe, and let's get started. In my previous videos, we covered limits and function continuity. Today we're going to be putting those two together to see how your function continuity affects the limits of your functions. Now, if you hadn't seen those previous 2 videos, no worries, you can find them both right up here. But if you had, you may remember that we covered 3 different function discontinuities. We had holes, we had infinite, and we had jump discontinuities. Today we're going to be covering each one of those 3 and seeing how they affect the limits of our functions. Now, limits for continuous functions were fairly straightforward. However, when you start throwing in discontinuities, you'll see very quickly that the waters get a bit muddy. You may also recall that we said the limit of a function at a particular point only exists if the left-hand limit at that point equals the right-hand limit at that point. We said it looked like this. We had limit as x goes to a from the left of f of x has to equal the limit as x goes to a from the right of f of x. We had to have this equal in order to have the limit exist at a. This is going to be very crucial because your discontinuities will often make this untrue. So let's start with holes and see what we got. If you recall, your holes will look something like this. This is going to be the x-axis, this is your y-axis, this is some a, and this is going to be some value that we don't know, it doesn't exist. So we're going to say this is a missing value, hence the hole discontinuity. Everything else exists, but this hole here at a, we don't know what that is. That lets us know that if this is supposed to be f of x, f of a does not exist. However, that doesn't mean that we have no limit for this. Remember, we're not concerned about what the actual value is at a. We're mainly concerned about how the function reacts, how it behaves. What is the function approach as x gets closer and closer and closer to a? And we have to approach from the left and approach from the right in order to have a limit. So let's see what we have here. If this was, let's say, the value b, right? This was the value b here. If we're approaching from the left, right, on the x-axis, your function approaches from the left here, and what does it approach? It's going to approach b. So you know that the limit of this function as x approaches a from the left is going to be b. You're approaching b. Yes, you don't equal b. You're not going to ever hit that. You're just approaching it. That's what the limit's about, not what it equals. Next, we do the same thing from the right. As we're approaching from the right on the x-axis towards a, we're going to be approaching from the right our function value to b. And you see that it also equals b. It's going to equal b as x approaches a from the right. Well, what does this tell us? Well, this tells us that for this whole discontinuity, we actually do have a limit at a, and it's going to be b. So the limit as x goes to a, not from left or right, combined, of f of x is going to be b. And that's not because we have the function equal b at that point, because we see it does not exist. It's solely because it's approaching b from both the left and the right. Let's check out this whole discontinuity we have here. Notice on our x-axis and our y-axis, we have this graph here, and we have a whole discontinuity at 3. However, you have a value at 3. What's the function value at x equals 3? Well, the function value is going to be, if this was supposed to be f of x, f of 3 is going to be what? 5, right? If you're plugging in, we have a hole here, yes, but we're defined here at 5. So f of 3 is going to be 5. This is why I said in my previous video that the definition I gave you for a continuous function was a very watered down basic definition. You need to know a little bit more about limits in order for you to get a more full, robust definition, because this is technically a discontinuous function. However, you exist for every value in its domain. So it kind of breaks that definition I gave you. But when you take into account limits, now we can have a more full definition. So we can say that a function is going to be discontinuous if there's a point that it's not defined at, or the left-hand limit may equal the right-hand limit in this case. However, it's defined at a very different point, or the limit doesn't exist. If any three of those things happen, then we have a discontinuous function. If you don't have any of those three, then your function is continuous. So once again, either you're not defined at a point, like our previous example. Remember, there was no value for our whole point in our previous graph. Or in this case, we see that we are defined. However, we're going to see that the limits are not going to be the same as the point that we're looking at. Or lastly, the limit doesn't exist, which you'll see in our next section. So if we did the same thing we did in our previous example, you approach 3 from both sides, right? And you notice that they're approaching this hole, which has a value of 3. So the limit as x goes to 3 from the right is going to be 3. And the limit as x approaches 3 from the left of f of x is also going to be 3. Lets us know that the limit as x approaches, not a, but 3 of f of x is going to equal 3. 3 and 5, not the same thing, but we're not asking for the same thing. This is asking for the value at 3. This is asking for the limit as x approaches 3. Asking for two different things. And you can have this and still be a function. You're simply a discontinuous function. Now that we talked about our holes, let's jump into our infinite discontinuities. Remember, when we're talking about infinite discontinuities, we're really talking about vertical asymptotes. And here we have a vertical asymptote at 0. So we're going to tackle this the same way. When you're talking about finding the limits, especially of discontinuous functions, you have to look at the left and the right hand limit. So as we're approaching, so the limit as x approaches 0 from the right of this function here, and the limit as x approaches 0 from the left of this function here, we're going to see how it reacts. So we're going to be approaching 0 from the right. What's happening here? As we approach 0 from the right, notice that we're getting larger. We're getting bigger and bigger and bigger and bigger and bigger. What are we approaching? And this is going to be infinity. We're getting larger and larger, and there is no cap. We're never going to get to a particular number because we're never going to hit 0. We can't hit 0. It's not continuous at 0. We're just getting larger and larger and larger and larger, meaning that we're just going to hit infinity, the concept of infinity. How about when we're approaching 0 from the left? Well, from the left, we're getting smaller and smaller and smaller and smaller. We're getting more and more and more negative. So technically, the magnitude gets bigger, but the direction is saying we're going in the negative direction. So we're getting closer and closer and closer to what? Negative infinity. So instead of infinity, we have negative infinity. Well, unlike our whole, here we have two different values for our left and right hand limits. What does that mean? Well, that means that for this infinite discontinuity, our limit as x approaches 0, just 0, not from the left or the right, just 0 of f of x does not exist. It doesn't exist if your left hand limit does not equal your right hand limit. This is a discontinuous function without a limit at 0. Now you have a left hand limit and you have a right hand limit, but you do not have an overall limit because your two parts are not approaching the same thing. Now that doesn't mean that all infinite discontinuities do not have limits. That's not what I'm saying. Here's another example. Let's say instead of the previous discontinuity we had this one. So this is still an infinite discontinuity, but notice that we have a little something different happening. The limit as x approaches 0 from the left of this function f of x, and the limit as x approaches 0 from the right of this f of x, they're actually going to be approaching the same thing. When you're coming from the right, you're getting larger, like we said. This time when you're coming from the left, you're getting larger as well. They're both going to be positive infinity, which means that the overall limit of our function as x approaches 0 does in fact exist, and we know it to be infinity. Now, obviously that doesn't equal an actual number, but the concept of infinity is plausible. It's perfectly fine to have this limit equal infinity. It just means that the function is going to be growing without bound. However, f of 0 does not exist. You don't have to exist in order to have a limit at that value. So let's jump into our last one, our jump discontinuity. Here we have a jump discontinuity, and notice it looks just like a step because that's what a jump discontinuity kind of looks like. You have a function and then you have another function. You can have multiple functions, 2, 3, 4, 5, it doesn't matter, but the key part of a jump discontinuity is that one function does not equal the other at its intersection point, which causes a break or a jump, which looks like a step as you're going from one function to another. And you can see for a jump discontinuity, you're pretty much never going to have a limit at your intersection point. And that's because you're not going to be a jump discontinuity if there's no jump. And the jump means we have a disconnect. Therefore, your left-hand limit has to be different from your right-hand limit. So let's say this was 5 and this was -5. The limit of this function, f of x, as x approaches 0 from the left is going to be 5, and the limit of f of x as x approaches 0 from the right is going to be -5. Doesn't equal means that the limit does not exist. That's by definition what a jump discontinuity is. So you don't have an overall limit, but you do have left and right hand limits. But that doesn't mean that all piecewise functions are going to have no limits. You can have a piecewise function and still have limits. And that's because you can have a continuous piecewise function. Perfectly fine. But when you start getting to jump discontinuities like this, then you're not going to have an overall limit. You'll just have left and right hand limits. So your whole discontinuity will always have a limit because it's a removable discontinuity. It acts pretty much like another function that's purely continuous, except at that particular point. So the limit is going to equal from both sides. However, your infinite discontinuities may or may not have a limit, but they're always going to be either infinity or negative infinity if it does have a limit. But your jump discontinuities are not going to be as lucky. They will never have an overall limit at that point. You'll just have your left and right hand limits. Well, I hope you were able to follow along with today's video, and I hope you now understand the role that continuity plays and whether a function has a limit or not. However, if you have any questions about what we see today, or even on homework, you can always put in the comment box below, or visit me on Facebook page at Tutor Me Sempai and tell me all about it there. If you hadn't done so already, remember that like. It surely helps the channel by letting YouTube know that you found the video helpful. And if you found the video helpful, so can someone else. So leave a like, hit the notification bell, smash the subscribe button, and share the video with a friend. Well, that's all the time I have for today. I'm really hoping this helped with your homework, and I'm looking forward to seeing you again next week. I'm Courtney, here's your playlist, and this has been another session of Tutor Me Sempai.